NENOMATICA, where mathematics meets YouTube excellence. Welcome to this math video. Today we're going to prove an important algebraic identity related to the product of two binomials. Let's look at our theorem statement. For all x, a, and b that belong to the set of real numbers, we want to prove that the product of x plus a and x plus b equals x squared plus the quantity of plus b times x plus ab. Now let's start our proof. We'll begin with the left-hand side of the equation, which is the product of the binomials x plus a and x plus b. For our first step, we'll apply the distributive property. This allows us to multiply each term in the first binomial by each term in the second binomial. For our second step, we'll simplify the products. X times x gives us x squared. X times b gives us bx. A times x gives us ax. And finally, a times b gives us ab. For our third step, we'll group the like terms. Specifically, we'll group the terms that have x as a factor. For our fourth step, we'll factor out x from the group terms. bx plus ax equals x times the quantity b plus a, which is the same as x times the quantity a plus b. Now, let's verify that we've reached our desired result. We started with the product of two binomials, x plus a and x plus b. And through a series of algebraic manipulations, we've shown that this equals x squared plus the quantity of plus b times x plus ab. This completes our proof. In summary, we've proven that for all real numbers x, a, and b, the product of the binomials x plus a and x plus b equals x squared plus the quantity of plus b times x plus ab. This is a fundamental algebraic identity that's useful in many areas of mathematics. Today, we'll visualize the factoring of expressions using geometric shapes, specifically looking at the formula open parenthesis x plus a close parenthesis times open parenthesis x plus b close parenthesis equals x squared plus open parenthesis a plus b close parenthesis x plus ab. This is a powerful way to understand algebraic expressions through visual representation. Let's start with an example. We'll use the formula open parenthesis x plus a close parenthesis times open parenthesis x plus b close parenthesis equals x squared plus open parenthesis a plus b close parenthesis x plus ab. Let's approach this geometrically by constructing a rectangle. Let's start by drawing a rectangle with width x plus a and height x plus b. The total area of this rectangle will represent the product open parenthesis x plus a close parenthesis times open parenthesis x plus b close parenthesis. The width of our rectangle is x plus a, and the height is x plus b. Now, let's subdivide our rectangle into smaller regions to better understand how the expression open parenthesis x plus a close parenthesis times open parenthesis x plus b close parenthesis expands. First, we'll divide it vertically at position x, creating two regions with widths x and a. Next, we'll divide it horizontally at position x, creating regions with heights x and b. This gives us four distinct rectangular regions. Now let's analyze the areas of each region. The top left region has width x and height x, so its area is x squared. The top right region has width a and height x, giving an area of ax. The bottom left region has width x and height b, so its area is bx. And finally, the bottom right region has width a and height b, resulting in an area of ab. The total area of the rectangle is the sum of these four regions x squared plus ax plus bx plus ab. Now, let's simplify our expression. We can combine like terms. Ax plus bx equals open parenthesis a plus b close parenthesis x. This gives us our final form x squared plus open parenthesis a plus b close parenthesis x plus ab. And this matches our original formula. Open parenthesis x plus a close parenthesis times open parenthesis x plus b close parenthesis equals x squared plus open parenthesis a plus b close parenthesis x plus ab. Let's try a concrete example to further understand this geometric approach. Let's set it equals 3 and b equals 2. Our formula becomes open parenthesis x plus 3 close parenthesis times open parenthesis x plus 2 close parenthesis equals x squared plus open parenthesis 3 plus 2 close parenthesis x plus 3 times 2, which simplifies to open parenthesis x plus 3 close parenthesis times open parenthesis x plus 2 close parenthesis equals x squared plus 5x plus 6. We can also visualize this concept in 3D. If we think of x squared as a square with side length x, AX is a rectangular prism with dimensions A1, and x, bx as another rectangular prism with dimensions b1 and x, and ab as a rectangular prism with dimensions 8b and 1. We can see how these pieces fit together to form the product open parenthesis x plus a close parenthesis times open parenthesis x plus b close parenthesis. This 3D geometric approach further enhances our understanding of algebraic factoring and expansion. Let's start with our first example. Our first example is x plus 1 times x plus 2. We'll use the binomial multiplication rule, which states that the product of two binomials can be calculated using a specific formula. First, we apply our formula. For the expression x plus 1 times x plus 2, we identify that it equals 1 and b equals 2. Substituting into our formula, we get x squared plus the quantity 1 plus 2 times x plus 1 times 2. Let's simplify this expression. We have x squared plus 3x plus 2. Now, let's move on to our second example. Our second example is x plus 2 times x plus 3. Again, we'll use the same binomial multiplication rule. For the expression x plus 2 times x plus 3, we identify that it equals 2 and b equals 3. Substituting into our formula, we get x squared plus the quantity 2 plus 3 times x plus 2 times 3. Simplifying this expression, we get x squared plus 5x plus 6. One more example, which involves negative numbers. Our third example is x minus 5 times x plus 3. We'll use the same binomial multiplication rule, being careful with the negative number. For this expression, we need to rewrite it in the form of our formula. The expression x minus 5 times x plus 3 can be seen as x plus negative 5 times x plus 3. So it equals negative 5, and b equals 3. Substituting into our formula, we get x squared plus the quantity negative 5 plus 3 times x plus negative 5 times 3. Now, we simplify the expression. Negative 5 plus 3 equals negative 2, and negative 5 times 3 equals negative 15. So our final answer is x squared minus 2x minus 15. Let's summarize what we've learned today about multiplying binomials. We want to expand the expression x minus 1 times x plus 5, using the formula for multiplying binomials. To use this formula, we need to identify the values in our expression. In our example, x minus 1, x plus 5, we have it equals negative 1 and b equals positive 5. Let's apply the formula. We have x squared plus the sum of a and b times x plus the product of a and b. So that's x squared plus negative 1 plus 5 times x plus negative 1 times 5. Now, let's simplify the expression. First, let's calculate negative 1 plus 5, which is 4. And negative 1 times 5 is negative 5. So our expression simplifies to x squared plus 4x minus 5. Let's look at another example. We want to expand x minus a, x minus b, using the same formula. For the formula, x plus a, x plus b, but our expression is x minus a, x minus b. We need to convert our expression to match the formula. We can rewrite it as x plus negative a, x plus negative b. Now we can identify the values in our formula. In this case, it equals negative a and b equals negative b. Let's apply the formula. We have x squared plus negative a plus negative b times x plus negative a times negative b. Now, let's simplify the expression. First, negative a plus negative b equals negative a plus b, and negative a times negative b equals positive a times b, or UB. Let's simplify further. We can also write this as x squared minus a plus b, x plus ab. Our example problem is to expand the expression 2x minus 4 times 2x plus 3. We need to find the expanded form of this expression. To expand this expression, we'll use the distributive property formula for multiplying binomials. This formula tells us that when we multiply two binomials in the form x plus times x plus b, we get x squared plus the sum of a and b times x plus the product of a and b. In our problem, we need to expand 2x minus 4 times 2x plus 3. We can apply the formula directly, but let's use the FOIL method to make it clearer. FOIL stands for first, outer, inner, last, which reminds us to multiply each term in the first binomial with each term in the second binomial. Let's begin by expanding using the FOIL method. First, we multiply the first terms. 2x times 2x equals 4x squared. Next, we multiply the outer terms. 2x times 3 equals 6x. Then, we multiply the inner terms. -4 times 2x equals -8x. Finally, we multiply the last terms. -4 times 3 equals -12. Now, let's combine all the terms from our FOIL method. The result of our expansion is 4x squared plus 6x minus 8x minus 12. We're not done yet. We need to simplify by combining like terms. 6x minus 8x equals -2x. So our final result is 4x squared minus 2x minus 12. Now, let's verify our answer by comparing it with the algorithm in the image. The image shows that when we expand 2x minus 4 times 2x plus 3, we get 2x squared, which equals 4x squared. Next, we have -4 plus 3 times 2x, which gives us -1 times 2x, or -2x. Finally, we have -4 times 3, which equals -12. Let's simplify the algorithm expression to confirm our answer. We get 4x squared minus 2x minus 12, which matches our final answer. Today, we'll be learning how to multiply binomials using the common term identity. This technique is especially useful when multiplying binomials that share the same variable term. Let's first understand the common term identity. This identity states that when multiplying two binomials that share a common term, we can use a special formula. The formula is, if we have a product of two binomials, ax plus b times ax plus c, this equals ax squared plus the quantity b plus c times ax plus bc. Let's solve our first example. Here we have the expression 2x minus 7 times 2x minus 3. Let's identify the parts to use with our identity. We substitute our values into the formula. We have 2x squared plus -7 plus -3 times 2x plus -7 times -3. This simplifies to 2x squared plus -10 times 2x plus 21. Or we can write it as 2x squared minus 20x plus 21. Let's move on to our second example. Here we have the expression 4x plus 5 times 4x plus 3. Let's identify the parts again. Step 1, we substitute our values into the formula. We have 4x squared plus 5 plus 3 times 4x plus 5 times 3. This simplifies to 16x squared plus 8 times 4x plus 15, which gives us 16x squared plus 32x plus 15. Let's work through one more example. Here we have the expression 2x minus 1 times 2x plus 4. Let's identify the parts once more. Step 1, we substitute our values into the formula. We have 2x squared plus -1 plus 4 times 2x plus -1 times 4. This simplifies to 4x squared plus 3 times 2x plus -4, which gives us 4x squared plus 6x minus 4. Let's summarize what we've learned about the common term identity. When multiplying binomials that share a common term, we can use the formula. ax plus b times ax plus c equals ax squared plus b plus c times ax plus bc. Here are some tips for using this formula. First, identify the common term ax in both binomials. Second, identify the second terms b and c. Third, use the formula to quickly find the product. We've worked through 3 examples. 2x minus 7 times 2x minus 3 equals 4x squared minus 20x plus 21. 4x plus 5 times 4x plus 3 equals 16x squared plus 32x plus 15. 2x minus 1 times 2x plus 4 equals 4x squared plus 6x minus 4. This common term identity is particularly useful when the binomials share the same first term, making calculations faster and more efficient. We need to expand the expression 5x minus 6 times 5x plus 2. Let's identify our terms. In this case, a is 5, b is -6, and c is +2. Now, let's apply our pattern. First, we'll compute ax squared, which is 5x squared. Next, we calculate b plus c, which is -6 plus 2, which equals -4. Then we multiply -4 by ax, which is 5x, giving us -20x. Finally, we calculate b times c, which is -6 times 2, equaling -12. So our final answer is 25x squared minus 20x minus 12. Let's look at our second example. Here we need to expand ax plus 5 times ax plus b. In this case, we have A as A and B as 5 and C as B. Now, let's apply our pattern to this example. First, we compute ax squared, which is ax squared. Next, we calculate b plus c, which is 5 plus b. Then we multiply 5 plus b by ax, giving us 5ax plus abx. Finally, we calculate b times c, which is 5 times b equaling 5b. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.